So this is the other one I wanted to do for you. Part D, evaluate the integral. What's different about this integral? It's called a definite integral when it has an upper and lower limit, right? So we have the integral from 0 to 1 of x times the quantity x squared plus 1 cubed dx. Okay, so you guys tell me then, what are we going to let u equal? X squared plus 1 is a good thing to try. And then du? 2x dx. So, all right, I'll show you two different ways to do this problem. My preferred way, and then the way that I was more comfortable with, the way that Chamberlain, who wasn't a math professor, was more comfortable with 20 years ago. So I'll show you the way I prefer these days. I see that my u is this guy. And by the way, I don't write this down. But this normally, if I were just going to evaluate this, I wouldn't write this down. But you got to get to the point where you're comfortable doing that. That guy would be my u, right? So I realize, oh, I almost have, if I include this x right here, I almost have a perfect du. By the perfect du, I mean 2x dx would be a perfect du if it were already there, right? Or 2x dx is my perfect du, in other words. So what do I need in front of that x to make this work?
2.
So let me rewrite the problem to look like this. X squared plus 1 cubed. I'm going to leave a little bit of space. I'm changing the multiplication around, putting the x over here, and then dx. You guys just told me I need a 2 right here, right? But so I put it there. But then that changes the integrand, doesn't it? So what do you have to do to compensate? Multiply by 1/2 or divide by 2. But can't I do that outside the integral symbol? Yeah, because multiplication by constants can be pulled inside the integrand, inside the integral and outside. So on the outside, I would just multiply by 1/2. So that's really the same integral, isn't it, that we started with, which is really important. But the point here is, okay, now this guy inside the parentheses is u, so this is u cubed. And then this guy right here is my du. So without actually making the substitution, I can just integrate x squared plus 1 cubed using the power rule for integrals, right? So if I were to write it down, it would be the integral of u cubed, right? Now, another reason why I don't write it down is because then you'd want to change the limits of an integration to fit what they should be for you if necessary. But so this is what's going on in your head again. So this is what I have over here. If I actually make the substitution, what's that integral equal to? Okay, so instead of actually making the substitution then, I'm just going to think, oh, that's my u. I'm going to add 1 to this exponent. Divide by 4. What do I have to not forget? Multiplication by that 1/2 out front. And then what do am I going to add anything? No. I'm going to evaluate, though, from 0 to 1, aren't I? Okay, now, no plus c because it's a definite integral, right? You only add plus c, because if you were to add a plus c, they would cancel out when you apply the fundamental theorem. So before you apply the fundamental theorem and plug in the upper limit of integration and the lower limit of integration, you could pull the constant out front and simplify actually as well. So you could think of this as 1/2 times 1/4, right? So what would you pull out front? So out of I call these evaluation symbols, out of the evaluation brackets or symbols, I would pull out that 1/8. Does everybody see where that's coming from? What's left inside? X squared plus 1 to the 4th. And so the point in doing that is when I evaluate this thing, I don't have to include the 1/8. I just keep that on the outside, and it makes it simpler. So if I evaluate this thing, okay, remember the fundamental theorem says you plug in the upper limit of integration first, right? So, okay, so I'm going to leave the 1/8 on the outside. What do I get when I plug a 1 in here for x and add and then take it to the 4th power? 1 squared is 1, plus 1 is 2, to the 4th power is 16. Let me change back to blue. Then what do I, and then minus, right, from fundamental theorem, f of b minus f of a, remember that? Minus what you get when you plug in the lower limit. What do you get when you plug in the lower limit in here? 0. Yeah, you get 0 squared, which is 0, plus 1, which is 1 to the fourth, which is 1, right? So you're going to get a minus 1 on the end. Does everybody believe that? Okay, so what do you get here then? Yeah, just 15/8. Remember, when you're evaluating a definite integral, you always get a constant as an answer, right? In this case, 15/8. In an alternate universe, an alternate reality, let's call it, maybe we would have done it this way. We could have actually said, hey, let u equal x squared plus 1. And then, as we previously observed, du is 2x dx, isn't it? And then the integral, I'll put in the limits of integration in a second. The integral becomes what? Well, just if we actually make the substitution, this guy becomes u cubed right there, right? And then we have x dx, we need 2x dx to have a perfect du. But if we put in a factor of 2 here, we better put in the 1/2 out here. And then, well, that's actually pretty easy. So you say, why not do it that way? Well, what do the limits of integration become? And remember, this in the original problem, this is x equals 1 for the upper limit and x equals 0 for the lower limit. So in order to find out the corresponding values of u, what do you have to do? Well, what would you do to get the lower limit? It actually isn't, well, I'll leave off that tidbit of information. But to get the limits, let's say it this way, to be a little more generic, to get the limits, you're going to plug in both limits into this little equation, this transformation equation you've invented here. But you better plug in the 0 if you're doing the bottom one. You better plug in the 0 for x because that's what x equals, right? So we'll say, usually we call the bottom one a, so we'll say a is equal to 0 squared plus 1, which is, of course, 1. And b, if we plug in 1, we get 1 squared plus 1, which is 2. So that this becomes, the limits of integration, if you actually make the substitution, become lower limit 1, upper limit 2. Well, then if you evaluate it, you'll get the same thing, so I'm not going to take the time to do that. But